All right, this is trigonometry. This is chapter 3, lesson 2, and we're going to apply radian measure in this lesson. And so we just learned in chapter 3, section 1, we learned about radian measure, and it's always kind of a stretch because everybody's used to degrees, and you're very comfortable with degrees. You know how big 30 degrees is or 45 degrees. And now that we've switched into this radian measure, we kind of want to justify it a little bit and show you, look, here's where you can use radian measure. So I want to show you one formula that's used quite commonly, and it's used with radian measure. And that formula is right here. It's a formula to find the arc length. And the arc length is if you have a circle, and within that circle, maybe you're curious about, on the edge of the circle, the length of a certain part of it. So if you're going on the edge of the circle, you cut off a certain angle, we'll call that angle theta. The arc length, if for whatever reason they abbreviate the arc length S, the arc length is this distance around the edge of the circle. If you think about that, that S, distance around the edge of the circle, if you went completely around the circle, you know what that distance is then, that arc length. That's called the circumference of the circle. But if you go on just a part of the circle, then we call that the arc length. So we have a formula here for the arc length. And the arc length, S, and again, I didn't give it S, that's just what we have to live with. The arc length equals the radius times the angle. Now the catch is going to be, you can kind of see we have it here. S is the arc length, R is the radius of the circle, and theta is the angle. The catch for this formula is it only works in radians. So at some point we might try to trick you, put it in degrees. If you ever see an angle measured in degrees and you want the arc length, then you need to immediately switch it to radians. And that was section 1. We talked about how you switch it back and forth. You know the conversion factor to switch from degrees to radians. You would multiply by pi over 180. So this is a nice formula to use when we're using radians because it only works when you are measuring your angle in radians. Okay, and again, just one little thing to hopefully help you remember it. Where did this formula come from? It came from a formula for circumference. And circumference of a circle, if you remember, the circumference of a circle is 2 times pi times the radius. And now that you have this new knowledge of radians, maybe that 2 pi jumps out. It used to be a number, and maybe now you're thinking, wait a minute, 2 pi, that's the angle. As a matter of fact, that's the angle if you turn completely in a circle. If you turn 360 degrees, that's the same as 360 degrees is the same as 2 pi radians. So all of a sudden, this formula for circumference, the distance completely around the circle, is the radius times the angle you turned. And then this formula, our arc length formula, is just a more specific version of that. The arc length is the radius times the angle that you turn. It's not always 2 pi because maybe you're not going in a full circle. Whatever part of a circle you turn in, you put that angle in there. So this is the formula we're going to use. Arc length is the radius times the angle. And I want to take you through some of the problems now that involve this formula. So let's start with some that hopefully are just nice and straightforward, and then we'll build our way into some that are kind of tricky. So first question here is find the arc length. You know the formula for arc length. It's the radius times the angle. In this problem, look, they give you the radius, 12.3. Look, they give you the angle, 2 pi thirds. And it's a simple matter of just multiplying these two numbers, 12.3 times 2 pi thirds. Whenever they want the arc length, it would be okay to use your calculator. Let's pull that out and see what we got here. So we have 12.3 times 2 pi thirds. We get an answer of 25.76. Maybe we can round that to the hundredths. All right, so that's our first one. The arc length is just the radius times the angle. How can you twist that around? Well, one thing you could do is, instead of asking for the arc length, give the arc length. Give you the radius. And I didn't put a question on here, but hopefully you can figure out the question. Question is, find the angle. Well, we have our one formula. Arc length is the radius times the angle. Our arc length is 7. Our radius is 3.2. And now I'm looking for the angle. To get theta by itself, I divide both sides by 3.2. Divide by 3.2, and I now need to know what's 7 divided by 3.2. Clear that one out. So 7 divided by 3.2, and I get an answer of 2.1875. It's an angle. I use my arc length formula, so I know my answer has to be in radians. So what does theta equal? 2.1875. If I don't put units on it, I know it's radians, or just to make it clear, I can write radians. And then just reminding yourself, a radian is about 60 degrees, a little less. So this is about 120 degrees. All right, same deal with this question. The arc length is 6. This time they give us the angle. Same formula. Arc length is the radius times the angle. We'll put our 6 for the arc length. The radius they don't give us. And again, that's kind of the question here. I should have been a little clearer about that, but that's our question. What's the radius? And our angle is 2 pi thirds. How do I get r by itself? I'll divide both sides by 2 pi thirds. That will give me the radius. If I want to do a little bit of algebra, I know how to divide. I multiply by the reciprocal, 3 over 2 pi. So it looks like 18 over 2 pi equals a radius. And at some point, it's okay to pull out your calculator. So let's look at this one. One kind of common mistake on this that's worth mentioning. I want to take 18. I'm going to divide by 2 pi. And it's very important here in your fraction that you put this bottom in a parenthesis. I put the 2 and the pi inside a parenthesis because I want to show that both things are on the bottom of the fraction. And this is the correct answer. So I get 2.86, and I don't have room to put that screen on here, so I'm just going to write that down. 2.865, if we round that. 2.865 is the radius, which is about, I forgot it already. What was it? 2.865. Thank you. And that's our radius. And just as a little bit of a side note, had somebody put that into their calculator incorrectly, had you put in 18 divided by 2 without the parenthesis in the pi, we get this answer, but it's incorrect. I don't think I can write on the screen. Let's see. I can't. It's incorrect. Let me just put it here. I can write it on this screen. It's incorrect because you wanted the 2 pi to be on the bottom. Your calculator is taking 18, it's dividing by 2, and it's multiplying by pi. So very, very important. A calculator skill here is you have to make sure the 2 pi is in a parenthesis. So this answer that you're seeing here is incorrect. The correct answer was 2.865 on that one. Oops. Take that away. Take that away. Take that away. And let's see. That takes care of our first page of these problems. Let's go on to a second page of problems with the arc length. So this is kind of our beginning problems. Move on to our second page. And this is a little trickier, these arc length questions. All right, find the distance between two cities. Assume they lie on the same north-south line, and if the Earth's radius is 6,400 kilometers. All right, so when we're doing a problem like this, we want to visualize, first of all, the Earth. And we're going to assume the Earth is round. That doesn't look completely round, but we'll work with that. We know here in the center we have the equator. And if we're measuring, if it's latitude or longitude, we know the equator would be 0. And then if we come up a little bit, 36 degrees, then we've got Los Angeles. So we've got that angle is 36 degrees. Right in there, so you can fit that in there, 36. And then further north is a city in British Columbia, so Pennington, British Columbia. And we're assuming it's due north, so if you drove north out of Los Angeles and just kept driving straight north, you'd end up in British Columbia at Pennington. And so we'll have that here. We'll just go PET. And that angle is 49 degrees. And that's the bigger angle from the equator up. Is 49 degrees. Well, if you look at this, we're trying to find the distance between Los Angeles in Pentington, we're looking for that little part of the circle. And again, assuming the Earth is round, which isn't too bad of an assumption, we're looking for the arc length. And so we pull out our arc length formula. We've got the arc length is the radius times the angle, and we're looking for the arc length. Well, let's see. What's the radius of the Earth? 6,400 kilometers. What's the angle? Let's be careful with this. We want the angle, but it's the angle from Los Angeles to Pentington. And so we know the latitude of Los Angeles was 36, Pentington was 49. So the difference between those two, 49 minus 36, is 13 degrees. So I'm going to put in here 13 degrees. Hopefully this is bothering some of you guys. Say, wait a minute, you can't put in 13 degrees. That is in degrees. This formula that we're using, arc length equals the radius times the angle, that formula right there, that angle has to be in radians. So we can do this all in one step. How do I switch from degrees to radians? I'm going to take this degree measure and I'm going to multiply it by pi over 180. And I can just do that simultaneously because that angle, again, right here, that theta, let's just remind ourselves of that. That needs to be in radians. So I've got my formula. I've got my radius here, 6,400. I've got my angle. Look at that. I've got the conversion right there. It is in radians. So let's get this distance now between our two cities. We've got Los Angeles and Pentington. And again, now it's a calculator question. Let's see what we get here. 6,400 kilometers. We'll take that times 13. Take that times pi. We'll divide it by 180. And again, the pi over 180 was to switch our degrees into radians. Let's take care of this. Let's get our answer. And we get 1,452 kilometers. So this is a nice application of our arc length formula and a nice reminder that if they give you degrees, even though it's something we're very comfortable with, if we're going to use the arc length formula, it has to be in radians. All right, let's go with one more problem here. Same type of problem, just a little bit trickier version of it. And you'll see this, all these kind of problems you're going to see on your homework. Okay, again, same kind of problem with latitudes here. We've got Charleston, South Carolina, Toronto, Canada. I guess I don't have the province for Toronto there, but it's certainly in the country of Canada. So Charleston, South Carolina, Toronto, Canada, 1,100 kilometers apart. They lie in the same north-south line. So again, we're assuming you're just going due north or due south. Charleston's at 33 degrees. Where is Toronto in terms of latitude? So again, maybe we sketch this out just kind of roughly at first, and I apologize if this isn't real neat. But we've got Charleston is at 33 degrees, and again, that's north of the equator. So that angle right there is 33 degrees. And that's Charleston. And then we know from our geography, hopefully, that Toronto is further north. So I'm going to have some city here, further north, Toronto. And what that angle is, I'm not sure. And actually, let me draw that a little better. Let's call the little angle in between those two, let's call that X. So that's the angle right there in between the two cities, which is the one we'll need. Because look, Toronto and Charleston on the surface of the Earth, we're looking for the arc length. All right, let's begin this. Arc length equals the radius times the angle. Our arc length is 1,100 kilometers, because look, they gave us how far apart the cities are in this problem. The radius of the Earth, remember what that was? 6,400 kilometers. And now we can find, I'm calling it theta here, it was x over here, same thing. We can find the angle between the two cities. So this is our theta, that's our angle between the two cities. All right, let's find this. Hopefully this isn't going to surprise you. It might. How do I solve for theta? Easy. Take 1,100. I'm going to divide by 6,400. And this will give me my angle. And that seems like a really small angle. And it seems like a small angle, 0.1718, was that a 75? Equals theta. Let's see what that was. Yep. That seems like a small angle until you remember, oh, wait a minute. That's in radians. But everything else we're doing here is in degrees. We got this 33 degrees northern latitude. We'll want to give the Toronto latitude in degrees. And so I want to take this angle and I want to convert this 0.171875 radians, and I want to convert it to degrees. So I'm going to multiply by 180 degrees over pi radians, because that's my conversion factor. So let's get this angle into degrees. So I take this, I'm going to multiply it by 180. I'll divide it by pi. And here is my angle. Now it's in degrees. So I get 9.84. Let's keep this whole thing here. Oops, try that again. If I was really good, there we go. Erase that line. Sorry about that. And we've got our calculations there. If I was really good, I would edit that out, but I think I'll just leave it just as it was. So theta is 9.85. And now that's degrees, so I need to label it. Okay, what do we find? Right here, the angle in between the two cities. Because Toronto is further north than Charleston, we take our 33 degrees, and we'll now add on the 9.85 degrees. And it looks like the latitude for Toronto is 42.85 degrees. And that completes the first part of our problems.